Cameraman is fine? Yes?
Yes.
First, a few seconds of respect for the Ukrainians who are still fighting for their freedom and for ours. Today, I want to talk about structure, peer-to-peer. Let me just set the stage. Small systems is what we saw in the beginning of the course. Small number of nodes and fixed number of nodes. We saw algorithms like broadcast and consensus. And this is important when building systems like databases. But when you have large numbers of users, it's very different. You have large dynamic number of nodes, unknown, always changing, huge. And we saw that the main technique is gossip. Gossip is the underlying bottom layer. From gossip, you can start from complete randomness and build order, like we saw, T-man, topology management. You saw a variation, a gossip algorithm called BitTorrent, where you have to introduce a new idea, which is economic incentives, because the nodes are selfish. Okay, this is a new thing. So the first one is gossip. This is unstructured peer-to-peer. Today I want to talk about structured peer-to-peer. The idea is that you build structure, it lets you get efficiency, a lot of efficiency, but you give up some of the robustness, okay? And today I want to talk about something called DHT, distributed hash table, which is widely used technique for doing that. So remember, gossip is completely robust, but it's slow, but it can work from completely random, and you will need it to bootstrap if you start from nothing. But afterwards, you don't always want to stay with gossip. You want to build structure and gain efficiency, gain scalability, but you give up some of the robustness. And DHT is a technique that does that. Okay? Today I want to talk about one particular way. I'm going to talk about peer-to-peer systems in general. Gossip is just one part of that. Then I'm going to talk about structured peer-to-peer systems. And they have logarithm properties, which means if you have n nodes, the lookup takes logarithm n, so it's fairly efficient. Okay? And I want to show kind of a general way of building these structured peer-to-peer systems using a principle called distributed k-area search. So basically, you have a tree, not binary, but k-area tree that kind of superimpose on the system. And we know that binary search is logarithmic. K-area search is just where you have k choices, is also logarithmic. And this is a very interesting way of building a peer-to-peer system. Okay? So that's what I want to talk about today. And I want to show you how it works. How you build a system that can repair itself, that can maintain itself. It's like a living organism. Any part of the system fails, it will repair itself, and it's efficient. It's more efficient than gossip. It's kind of like living organisms take advantage of order, biological organism, to gain things like efficiency. Here we see the same. I'll show you some optimization. I'll show you how to use this for building applications, algorithms, services, broadcasts in particular, and as a general way of an infrastructure for building applications. Okay? So I'll first talk about, I'll give you a first kind of history of peer-to-peer, 3 generations. Then I'll talk about distributed hash table, the principle, DHT, and then the DKS, distributed k-area search. This is the one that's designed according to a principle. It's good to design systems based on principles. you have good confidence that they work, you understand them. And then I show you how to do broadcast in this. So this is much more efficient than gossip broadcast, because we take advantage of structure, okay? Kind of the general lesson now. If you want efficiency, you need order, you need structure, and DEHT and DKS, they give you structure, okay? And we actually made applications. So we actually had a research project doing this, and we built some systems called Scalaris and BeerNet and some applications. We actually had a distributed Wikipedia, a huge application, and it even won a prize. This was in 2008. It won a prize on scalability from IEEE. So this is actually really nice architecture. Okay, so let me give you history of peer-to-peer. First of all, what is peer-to-peer? In the early days, people didn't really understand. Gossip is peer-to-peer. Peer-to-peer means there's no server, there's no client. All the nodes are equivalent. That's peer-to-peer. But here's a definition from Aura. This one is peer-to-peer is a class of applications that takes advantage of resources at the edge of the internet. So what is the edge? Well, the edge is the opposite of the center. The center is the database, the data center is the cloud. So everything which is farthest away from the cloud, the logical frontier, that is the edge. And also the edge is very unstable, and it's very easy to disconnect devices in real life, in the real world. Okay? And it may not even have IP addresses. It must operate outside the DNS system and have autonomy. So this is one way of looking at peer-to-peer, that it's at the edge. Okay? Outside the data center. Here's another definition. Peer-to-peer is sharing of resources between systems. Direct exchange, no server. Two nodes, they talk to each other. There's no server. Okay? And then this is a great phrase because it comes from typical management speak. Peer-to-peer computing takes advantage of existing computing power and networking connectivity, allowing economical clients to leverage their collective power to benefit the entire enterprise. Sounds very impressive. This is a typical management thing. So the idea is that it's economical. You have all these resources that are decentralized that can work together. Okay? But actually, taking a step back, this is kind of our view. Peer-to-peer is a form of distributed computing, okay, with resource sharing. That means the nodes will share their resources, like in BitTorrent. All nodes are both client and server, same rule. There's no special server, no client. All the nodes do all the work. Decentralization, that means there's no servers, again. All the nodes are equivalent. And scalability means the number of nodes does not matter, it keeps working. And also it's robust. Because the number of nodes is very large and changing, the system has to organize itself. Self-organization is robust. Okay, so we're going to see how self-organization works. Okay? So first a little history. This is, for most of you, this is ancient history, but I remember this. This was an application called Napster, you may have heard of, which was doing file sharing. So here you have a bunch of people with files, movies or whatever, Britney Spears, whatever, and they want to exchange the files without paying any money to anybody. And in Napster, they would exchange the files between themselves, but in order to find out who had the file, they had to go to a central directory. So the directory was centralized, so it wasn't completely peer-to-peer, but it was almost peer-to-peer. This one was killed very easily by just shutting down the central directory, it dies, okay? So this illegal file sharing was stopped. But then the second generation came. Here you have random overlay networks, no central directory. In fact, every node has both storage and directory, but it only knows some of the system. Nobody knows everything. So if I want to search for a file, I have to do like lookup, and it will do flooding. It will go into the network, it will follow the neighbors for a certain distance, but not everything. It's too far. Maybe 100,000 nodes, and then see whether somebody has the file I want. My favorite singer, Britney Spears, for example. And then once they find it, they can do the exchange directly. So there's no central node here, and there's still many systems that use this principle. They're just random nodes connected together. Nobody even knows the whole system. And the lookup is done using kind of random up to a certain depth. It's pretty random, but it works pretty well, actually. And there were systems called Nutella, Freenet, and now there's lots of derivatives of that. So this idea is still used a lot. And there's no way to kill this, okay? Unless you set up a whole firewall, like you installate China from the world, yeah, then you're great. But barring that, you cannot kill a system like this. But the problem of this is not so efficient. It's doing random flooding, so it's really inefficient. And at some time, 10 or 15 years ago, 50% of the whole internet resources was being wasted on this kind of application, okay? Or more, depending on where you look. Of all the internet resources, that most of it was be doing this kind of lookup flooding. That's how inefficient it was. But so that's one reason why this is, it kind of moved over to something structured. And this is the distributed hash table abstraction. This idea is the basis of most of the structured versions. So you have a put and a get. You have a hash table stored over many computers, and you can do put or get operations. Okay? You can do, you know what a hash table is? A hash table is a mapping from keys to values. And you can put values in, you put the key and the value can be a file, it can be a big thing. And the key can be the name of the movie, for example, and the value can be the movie, a big MP4 file. And get key will get the movie. And these computers are connected together somehow. And when computers crash, it somehow reorganizes itself. So this is nice, huh? It's very easy to use, and you can build applications on top of this. So you can see that this is kind of a nice idea. So how do you do that? These can crash. Also, you want scalability, so the movies have to be kind of spread out over all of them. And if you ask for one computer, you do a get for one computer, but the movie is actually stored somewhere else, it actually has to do internal routing, okay? So there's some structure here. So what is it? How does this magic thing work? That's what I want to explain today, okay? This idea, distributed hash table, is a very strong idea, and you can build peer-to-peer, self-organizing systems that implement that. That's what I want to show. And it's very conceptual. So I'm going to start very abstractly. Okay? And this was a huge research topic. So here we see a number of systems: core, pastry, tapestry, Canon, Cadelia, Pigrid, Viceroy. There's a whole bunch of systems. Many people were building these kind of systems, but the first one was Port, which invented this idea in the year 2001. Okay? This is the conceptual idea. You have computers on the nodes, and you have the values, which are like the files. How do you store files on computers? Well, each of these computers gets a key, a special, unique identity. These keys here. Each of the files also gets a key, a special, unique identity in some space, maybe 128-bit vectors. So you see these two very separate things. The computers and the files, they will live in the same space. Okay, that's the key idea. These two things are in the same space. And then, in this space, you do kind of a cluster. This key here, this circle is a computer. These little squares are files. And the file is stored at the computer, which has the closest distance in the space. So you kind of do this clustering. So this node will store these files, this node will store these, and so on. And if the keys are determined in a kind of mixed pseudo-random way, this will be balanced. Each node will have approximately the same number of keys, so it's completely scalable. See, so this is the idea. And then what we do is we connect these nodes according to some topology. Like we saw in TMAT, maybe they're connected like a mesh, or a ring, or a cube. These nodes are then connected and they will route. Okay? So that's the idea. So this you have to remember. Identifier space, and both the computers and the files are living in that space. Okay? Yeah? Question? No? Okay. So that's the idea of a distributed hash table. So here's kind of a picture of how it works. So here I have a hash table, which you know, it's a mapping between keys and values. Here it's very simple, numbers and words. It can be names of movies and the actual movie itself. Now this can be gigabyte files data, which is usually the way it's done. And they are mapped. So here we have 4 nodes. So assume that part of the hash table goes on node A, part of it goes on node B, part of it on node C, and part of it on node D. Okay? How do we do that? We'll see. And the basic service that this system gives you is a lookup. That means if you give the key, you can look up the value. And you can ask any node and it will do the routing. Okay? That's the basic idea. Okay? Each node has a routing table that has pointers to some other nodes. And if you do it smartly, the number of hops will be constant or logarithmic in the number of files. So you understand the idea. So each node has its own identifier, and the keys that are somehow close to that node will be stored there. Okay? But you can do the lookup from anywhere, and you will route. Okay? So for example, if I am at node D, and I do lookup 9 is stored at node A, then I will do a routing. For example, I will jump to node B and A, and then I will do the lookup. Okay? You see how it works? Identifier space, nodes and items, the hash table, and you map it onto the nodes, and then you do routing. Okay? But now the trick is, how does that really work in practice, this routing? Okay? It's a nice idea. How do you really do it? Well, the chord system, they give a solution, and this was a really nice solution, and this solution has inspired many, many, many systems after. So this was kind of the first real system. The IDs, you arrange them in a ring. So here we have a ring from 0, 1, 2, all the way up to 15. So you see it's 4 bits, huh? 4-bit. Simplified. Usually it would be like 128 bits and very sparse. Okay? And the ID, and here you have both the computers, which are circles, and the items, which are flats. So for example, this computer has ID 3. This computer has ID 4. And there's no computer with ID 5. There's just not enough. There's no computer with ID 11. Okay? There is a computer with ID 6, 7, none with ID 8. There's one with ID 9. And then you also have the files. There's a file with ID 2, file with ID 8, file with 9, 12, and 13. Okay. Now this looks pretty full, but in fact in real life it's very sparse. Huh? You have a huge key space, like 128 bits. So most of the numbers, there's nothing there. Huh? Okay? You have a few nodes, and if you add nodes, you can add nodes, and you have a bunch of items, and they're all kind of spread out. Okay? And now we will map the nodes to the computers. We will map it. So, for example, the item 2 will be stored at node 3. So every item is stored at the next, the closest node that exists. So this and this will be both stored at 9. The files 12 and 13 will be both stored at node 15. Okay? And file number 2 will be stored at node 3. And nodes 4 and 6 and 7, nothing is stored there. They're empty for now. Okay? See how? So you map. The way the mapping works is that each item is stored on the node that comes next. So this one's stored at 9. This one, the 8, is stored at 9. There's nothing stored at 10. See how it works out? Okay? So this is how Chord maps the items to the nodes. And now I'll show you how the routing works. So let's say I'm at node 1, and I want to get 15. I want to get file number 15. Well, this whole thing is completely decentralized, so I don't know where it is. Huh? Node 1 does not know where it is. But it knows how to get closer. Okay? So file number 15 will actually be stored at node 0. But the routing will always go clockwise in Chord. And you have, each node has 4 links. Well, 1 link for every level, so a 4-bit space. Huh? Here you have 4, if you have 128, then you will have 128 links maximum. So what do you do? I'm getting 15, I'm at 1. Well, I will go to the highest number that is less than 15. You see, I'm always increasing the number, huh? So I will choose one of these 4 routing links to get closer to 15. But 15 is really very big, huh? So this node, this link, so then there will be a link to 3, another link to 3. The link to 2 doesn't exist because there's no node there. It's also 3, huh? So you have 3, 3, 6, 9. Those are the routing table entries at node 1. 3, 3, 3, 6, 9. And you pick the one that's the greatest that is less than 15. Well, that's 9, huh? So you go to 9. So I send a message to node 9. Okay? That's the first stop. And now I'm at node 9. And I still want to get 15. Well, I also have a routing table at node 9. Node 1, 2, 3, 4. This one goes to 10. This one goes to 14. This one also goes to 14. And this one goes to 1. So I want to go to 15. Well, the one that goes farthest and it is less than 15 is this one. It goes to 14. So I'll follow this one. Okay, that's the second hop. Okay, so I'm at node 14 now. And now I want to go to 15. Again, I have a routing table with 4 entries, going to 0, 0, 3, and 6. See that, once like that. But the 0, 15, so it wraps around, modulo. So 15 will be stored at 0. So that means we follow this second link, and then we're done. That's a 3-hop route, okay? You see, it's completely decentralized. We don't have to know how many nodes there are at all. There could be millions or 100,000 or 1,000. But so the routing is always the same. Each node routes only with its local information. Okay? So the routing is like this. From node 1, you have 3 hops to node 0. So from 1 to 9 to 14 to 0, and then we found 15. So this gives us logarithmic routing. Okay? It turns out for 16 nodes, the maximum is 4 hops. We get 4 hops when you have everything is filled up. So here you have only 3, because there's really not that many nodes, many empty ones, okay? But if they get kind of filled up, you can get up to 4, which is log base 2 of 16. So you see the number of hops, that's the maximum, but the actual maximum is the log base 2 of the number of nodes, which is much less than the total size of the identifier space. So you see how with this, we understand how to allocate the items to nodes, and we know how to do routing. So the questions, how do we build this hash table? I've answered them. You see, it's very simple, actually. Yeah? Of course, what happens if the node crashes? Or if new nodes come in? Well, I will show you that this system can repair itself so that it always keeps the structure. I'll show you how that works. So this system will always be repairing itself to maintain this structure with logarithmic lookup. Okay? See how that works? It's neat, right? And very efficient. Okay, now that we take a step back, there's basically 2 kinds of peer-to-peer system. The unstructured, which is the worst one, is the gossip. But in terms of file sharing, we have these the hybrid one, which was Napster because it had one directory. The Nutella fully decentralized, and we also have half and half. We have a small number of directories, maybe it's for efficiency, but still more than one, so it's still decentralized. And then you have the structured ones, like I just showed you. And there's a whole bunch of them, but the principles are very similar, so I'm only going to show you this one, core, and then a kind of evolution of this one called concatenous. Okay? So there's a lot. So here's a table comparing these. Napster, Nutella, pastry, tapestry, chord, scalable. Chord is scalable because if the number of files increases and the number of nodes is proportional to the number of files, it will work no matter how many there are. The amount of files stored in each node will be bounded and the routing will always be logarithmic. Okay? So you have a high guarantee to get there, very robust. Okay? The routing table size is log n. Okay? And then this is the speed. Read, insert, delete. It's all logarithmic. Okay? It's not perfect though. There's no locality because you may be hopping, but in the real world you might be going from Europe to Japan, back to Europe to Japan. So it's not in the way I showed here. The DHT does not map to the geographical locality. That's kind of a disadvantage. But there are versions of it where it does. It's a little bit more complicated. You can manage it so that you arrange it so that you can take locality into account. But but I won't show that, but that's possible. Okay, so this, the other ones I'm not going to talk to you, just to show you that they're all kind of efficient. Okay, but I want to show you now some things. I want to show you a general framework. I want to show you how to maintain this thing. So when nodes crash, when new nodes come in, the system has to repair itself, like a biological organism. Huh? The routing tables, it has to keep repairing it down. So it's like always converging. Such a system, there will always be failures. So the routing tables will never be absolutely perfect. But they will be almost perfect, and they will always be converging towards a perfect one. It's like human being, huh? Everybody has some kind of problems. I just got a tooth repaired. Sometimes you fall, you get sick, sometimes you break a bone. It's very rare that a biological organism has nothing wrong, completely nothing wrong with it, okay? But that's okay, because the organism is always repairing itself. So here's the same. Okay? You can also do queries. I've only shown you lookup. You can do more complicated queries, like intervals, like real database queries, if you do it smart. And this thing is very robust. You can also do broadcast, group communication. So I will show you the right ones. I will show you. The locality I will not show you. Heterogeneity. If some nodes are very big and some nodes are very small, then you have to change. Maybe put many links on the big nodes, but I won't talk about that. So only talk about the 4 red things. That's all I want to talk about. And this is actually something that we did research on. So this is something that was a research project, but it's very nice because it's very principled. So the principle is very simple. So here's the basic theoretical principle of the lookup. Okay? So the ring I just showed you, I show it as a line here. Okay? It's actually this ring. And the nodes are the balls on there, and the rest is empty. So the ring I just showed you, I just split it as a line. So how does the lookup work? It's like convergence. So in the beginning, I'm at node S, and I want to do a lookup. I want to look up origin. In the beginning, I don't know anything, so the value could be anywhere. But I want to converge the interval of uncertainty. Okay? So when I do one step of the lookup, okay, let's say I have a bunch of choices here. Each time I do a choice, I reduce. Okay? So I'm looking for node 15, or I'm looking for some file. I don't know where it is. When I do one step of the lookup, I've already narrowed down the result. In fact, here, this is k-area search. So here it's equal to 4. Chord is like a binary tree, yeah? K is equal to 2. This is a more general thing. Each time I do a step, I divide by 4, or by k, the uncertainty, until the uncertainty is 1 node. So this is the first level lookup, and let's say it goes here. So that the lookup table only needs k minus 1 entries, because maybe the lookup says I stay at the same node, that's the dotted line, or it goes to another node. So if k, I only need k minus 1. Here I have k is equal to 4, and I have 3 jumps. The next step I have 3, and so on. And it keeps getting narrower and narrower until I'm at log k n, and there I find it. Okay? So chord also is an example of this, with k is equal to 2. This is more general. Here we're looking at a general kind of convergence scheme. Okay? Each of these intervals has one node, which is what we call the responsible node. So it's kind of the node that you go to from outside when you go into that interval. Okay? You're always going to the same one, not to some random node, you go to that one, and then it keeps going. And each of the variations of our algorithm will have something like this. Chord, okay, responsible node is the successor, and then we have other systems which I will not explain, but the concept of a responsible node is everywhere, okay? Okay, so here's some intuition. So let's say we have n nodes, 10,000 computers. Each of those nodes has some information, okay, has a routing table, okay? And the bigger the routing table is, the shorter, the less hops we need, because the tree is wider and is not as deep. With binary tree, you have log 2n, but if you have k is equal to 4, it's log 4n, less hops. So there's a trade-off. Big routing tables give you short lookup. Small routing tables give you longer lookup. Okay? And the extreme cases is where every node knows about everybody else. That's not very scalable, but for a small system it might be good. Or the other worst case is every node only knows about one other one, and then you just have a ring. That's really not efficient, but it needs almost no space. So you can actually make some kind of a computation. You have 3 numbers that you can play with. You have n nodes. You have the number of hops, h, and the number of entries in the routing table for each node. So that's like the space of the routing table. So the number of hops maximum is log base k to n, right? That's logarithmic. The number of routing table entries, well, you have log kn levels in the tree, and for each of these levels, you have a bunch of routing table entries, k. But actually, only k minus 1, because one of them is just staying in the same place, so you don't need to waste space for that. So it's k minus 1 times log base kn, and if you eliminate k, you can get a relationship between the 3 values. Okay? So this shows you how, if you increase r, how h decreases. Or if you increase h, how that r is smaller. So this is the relationship. It's this funny exponential, Okay? So this is just to show you, but the intuition is that routing table and hops are kind of inverse, Okay? So chord, the one I showed you in the beginning, is actually a binary search. Okay? So the number of nodes, the number of hops is log 2n. The number of routing table, k is equal to 2. So k minus 1 is equal to 1. So the size of the routing table is log 2n. So here we have 4 entries in the routing table, 1 for each level. You have the longest one is for the biggest level, when you divide half and half. The second one is 1/4, 1/4. The third one is 1/8, 1/8. And the fourth one is 1/16, 1/16. Okay? So here's another way to see it. Some people find this intuitive. Your mileage may vary. I start at node 0, and I make a choice. And I either go to 0 to 8, or 8 to 0, which is the other side. And then I'm there, I go from 0 to 4. When I go to the first half, so I first choose the first half, then I go to the first quarter or the second quarter. If I'm at the first quarter, I can go to the first eighth or the second eighth. And eventually I end up at the nodes. Okay? So the idea is k-array searches are more general than chord, and and it's kind of a very nice principle. It's a general way, and k is like a parameter. Okay? So, let me say something about the size of the routing table. Well, why do we want small routing tables or big routing tables? Well, in fact, the size is not going to be so big. The logarithm of n is small. If I have 100,000 nodes, or 1,000,000 nodes, then the log base 2 of 1,000,000 is 20. And if k is equal to 4, then k minus 1 is 3. 3 times 20 is 60. So I have 60 routing tables entries for 1,000,000 nodes. It's not very much, So the routing table, the actual size, has nothing to do with storage capacity, because they're always going to be small. There's two reasons why we want to have big or small routing tables. One is the number of hops. There's a trade-off. The bigger the routing table, the smaller the number of hops. But you might say, great, let's just have huge routing tables since they don't take almost any memory. But then there's another thing, the second reason. When there's a mistake in the routing table, you have to fix it. And the bigger the routing table is, the more work it takes. So there's like a trade-off. You can have a routing table with k is equal to 100. That means up to 10,000 nodes, you only have 2 hops. But these 100 links, there can be mistakes in there. You'll always be fixing the routing table. And that takes extra messages also. So you'll always be kind of fixing it. Maybe that's okay. But maybe because you want to have only 2 hops, but maybe you want to have a very simple routing table and easy to manage. But then you have to have more hops. Okay? So you see the idea how it works? You have this convergence idea with the routing tables. Okay? So let me show you now DKS, a real system. So this is another system which is a variation on chords, more general, more realistic. So, which is called DKS, Distributed K-Area Search. Okay, so this is a peer-to-peer system, and it's a real system. So it's really built, and it's really practical, and it works. And so it has to do things that a real system has to do that is not in the theory. For example, when a node joins, what if 2 nodes try to join at the same time in the same place? Well, you have to be careful that there's no race condition there. So that means the joining has to be done specially so that it's atomic. That means if 2 nodes try to join, it will be serialized. Okay? Or if 1 node tries to join and at the same time a node right there is failing, again it has to work fine. Okay? Also, the DKS has techniques for fixing, really repairing the routing tables that are efficient, avoiding unnecessary bandwidth consumption. So I'll show you how to fix the routing tables. Okay? So this is an actual article, but I won't. This is actually a research work. And I'll explain how it works. There's 4 principles, but I will only show 3 of them. First principle, it's using distributed K-area search. That means each time we route, you're like converging smaller and smaller intervals. It does the join and the leaves using the atomically. So it's very practical. It's never going to get messed up when you have many joins at the same time. And it has an efficient technique for repairing. This is actually very neat, which is called correction on use. Okay? Which means that, routing tables will always go bad, because in a system like this, nodes are always joining and leaving. It's always in a flux, such a system. If you have 100,000 nodes, like peer-to-peer, file sharing, always nodes will be going in flux. So my routing table is slowly going bad. Always, huh? The links in there, maybe I will point to a node that has crashed, or I point to the wrong node because a new node comes in, okay, and it should be pointing to the second one. So it will kind of be going bad slowly. So you have to fix that, and you can't wait so long. So there's two ways to fix it. One way is to always check all the routing table entries. And if there's any mistake, fix it. So route, and if you see it's going to the wrong node, send a message back to fix. And you're always doing that. It's called periodic stabilization. That's not efficient, right? You're always doing this extra work. So another way is to fix it while you're doing the normal work. So if I do a lookup, a regular lookup, and the routing table has gone bad, then the lookup will be going slightly wrong. It won't be completely wrong, it'll just be less efficient. Eventually I will get there, because it's converging. I will get there, but it will take longer. And I notice there's a mistake. Maybe there's a node that's crashed, for example. When that happens, then I send a message back to the node that did the lookup to fix. But this is doing the normal lookup. It's called correction unused. So you're always fixing the routing tables while it's the normal working. Okay? So those are the three principles. Okay? So then you have the DKS, the atomic join and correction unused. So the DKS means you can choose the value of K. You can tune the routing table size. So you have like tuning ability to tune it to make it faster. Right? So principle number one, you have ability to tune it. You change K, you can also change, so the changing of the K will change the routing table size versus lookup length. There's also fault tolerance degree, which I won't talk about. So there's replication. So the real system has replication, which I won't talk about, which the files are stored in multiple places. If one of them crashes, it's still in other place, which I won't talk about, but that's also tunable. Then you have the atomic join and leave. So this one gives you a strong guarantee. And then you have correction unused, which fixes the routing table with no extra messages. So this is a real running efficient system. Okay? Okay, let me make a small break now, clear the pools, and then I show you how it works after. It's kind of like a biological organism, okay, which is always repairing itself, like a cell or multicellular organisms. And some very simple organisms like earthworms, they will have similar behavior to this. Okay? But let me show you DKS, which is a variation on the chord. It's nice to see the variation. So here again you have a ring. Again, let me just show for 16 possibilities. Okay? And you have a hash function. And you have the nodes, which are the computers, and then the files, okay? And each of these maps to a number. And the files will go to the next number on the ring for which there exists a computer, okay? An item is stored at the successor. The successor is the first node that follows on the ring in the clockwise direction. So this file, which has a hash of 13, will be stored at node 0. Because there's a computer there. 14 and 15, there's nothing there. Okay? And the node the file that hashes 15 to 15 will also be stored at 0. Okay? So that's same as chord. Now, DKS is a real working system, so it has some extra things that we did not see in chord. First of all, it has a linked list. All the nodes are always connected to the predecessor and successor. Every node knows its successor node here, the light gray, and its predecessor node, the blue. So even if there are no routing tables whatsoever, you can still route, but it's slow. Okay, so that's very important. Remember I told you the routing tables will slowly degrade in any real system. Well, this design says that no matter how degraded they are, we can still route. So the routing tables are just an optimization. Of course, they're a really important one, but they're not absolutely necessary. That means we can still repair them even if they are very degraded. Okay? Because of this, we can always route using this predecessor successor. Okay? And these are maintained. Of course, this can also go wrong, predecessor successor. In the real system, each node will have multiple successors and multiple predecessors, which gives you a resilience, a fault tolerance, which I won't show here, but you can assume there's multiple predecessor and multiple successor. Okay? Okay? So remember, I showed you three principles here. DKS, atomic join leave, and correction on use. So let me show you the principles. The first principle is the distributed k-area search. This is a convergence in the search. Okay? Okay, so if you add a routing table, the routing gets much more efficient. You don't need it for correctness, but for efficiency, and it goes to log base k n. So in each node you have a routing table containing log base k n levels, and each level has k intervals. So you start from the whole ring, then you divide by k, then you divide by k again, again, and again, until you converge. Okay? So the routing table has levels, and at each level it has k intervals. Okay? So it has level L and interval I. It starts by your level 0, there's only one interval. Then you go to level 1, you have k intervals. Then level 2, you have k for each k again. So you have log base kn levels, and at each level you have k intervals. Okay, so k times log base kn, or actually k minus 1, because one of them will be staying at the same node. So let me show you an example. Okay, so node 1 here. Look at node 1. So here we have a DKS. So the red ones are the computers. Okay, and then there's files. So these little dashed purple arrows. That's the files that are stored there. So file 5 is stored on 6, and so on. Okay. So let's look at node 1. So there's the first level is you divide the whole ring into 4 quarters. So you have the whole ring. 4 quarters means 3 things. The fourth one actually stays here. So the fourth one is this quarter. The first one is this quarter. This one will be this quarter, and this one here will be the final quarter. So the first level divides the whole ring into 4 quarters. Okay? So that's level 1. So the level 1, so the entry 0, 1, 2, 3. Yeah? The first one will stay at 1. The second one will go to, it wants to go to 5, but it will go to 6, the first node that exists. The third one will go to, it wants to go to 9, but the first one that exists is 10, will go there. And this one will go to 15. Okay? So that's the first level. And then there's a second level. So each of these 4 quarters is also divided into 4. So I'll show you just one of them. The first quarter, but it's the same for each of them. if you stay at this border here, the second level, which is the green one, will go 1, 2, 3, 4. But 4 doesn't exist, so it will go to 6. Huh? And 1 exists, stays at 1. There's a node at 2, there's a node at 3, there's none at 4 or 5, so the fourth one will go to 6. Okay, so those are the 4 entries of the routing table. 1, 2, 3, 6. Okay? So the lookup basically starts at level 1 and goes to level 2 and so on. Okay? So it's actually very easy. It's called interval routing. It's actually something similar is actually done in IP. Okay? The lookup is if the key is between my predecessor and me, then I'm done. If the key, so let's say I'm here, and the key is between my predecessor and me, that means the file. That means it's already stored here. That means I'm there. Okay? I am where the file is. So that means I'm done. Otherwise, I just follow the next level. I follow and I look at the level, the least one, which is higher than the value of the key. Okay? That's it. So it's actually very simple routing. Huh? So here's an example. I'm at node 0, and I went, so again we have some nodes here, and we have some files, not so many, very simple here. Level 1 is the blue, and level 2 is the yellow. I'm at node 0, and I want to go to 11. Okay, so what do I do? Well, this is going to 4, actually to 6, which is less than 11, so I'm not going there. This is going to 9, so it's less than 11, so I'm not going there. This one, it's the highest one that is less than 11, so this is going to 9. This one goes to 12, so that means it goes here, okay? And so I'm there, I'm at 9. And the next step is I'm at 9. So here's the tree from 9. So every node has a tree with 2 levels. Huh? So the red one is the first level, and the gray one is the second level. Okay? So now I'm at level 2. So if I look at the links here, the highest one is that I need to go to is this one here, is to 12. Okay? And this will solve the routing in 2 hops. Okay, so basically from 9, I will not follow this because it goes to 0, it's too far. But I will follow this one because it doesn't go too far. Okay, so that's the routing. It's similar to chord, only here we explicitly show the shrinking intervals. Okay. Chord is actually doing this for k is equal to 2, if you look at it. But here we have k is equal to 4. So that's the first principle, huh? That's the routing. The second principle is the atomic action. Here I won't show the detail. Let's say we have new nodes coming in. So in this kind of a ring, which is doing like file sharing, you always have new nodes trying to connect, and you have also nodes leaving, crashing or leaving nicely. So you need to have an operation letting a node join or a node leave. So how does that work? Because those new nodes have to have routing tables, they have to have predecessor and successor pointers, and if you have concurrent joins, they have to not interfere with each other. Okay? So, there is a protocol. When I join to a node, I know the predecessor and the successor node, so I have 3 nodes, 2 nodes on the ring, and the third one wants to join. So I have to update the predecessor and successor pointers. So there's a protocol that does that I won't explain to you here, using locking and so on, so that the operations do not interfere, even if you have concurrent joints. So it involves 3 nodes if there's no failures. If there are failures, then you might have to go to a further successor, which I won't explain here. And what about the routing table? Well, the new node will get a copy of the routing table from its successor that was on the ring. So that's not completely right, because it's one step different, but it's almost right. So the new node has a slightly degraded already routing table. And this slightly degraded one will be fixed using the technique I will show you, okay? Using the general technique for repairing the routing tables, okay? So if you have concurrent joints, they will be serialized. As usual, atomic actions are serialized. Okay? So let's say here, let's see. Here I have a system. 1, 2, 3, 6, 10, 12, and 15. And assume that a new node comes in, node 14, here. So what does that mean? It means that the routing table for node 1 has to change. The third link here used to go to 15, but now it has to go to 14. But it doesn't know that. When node 14 is added, this routing table will be incorrect. Okay? Because it will go to 15 and not 14. Okay? So node 1 pointer on level 1, third interval becomes invalid. But so far it does not fix. It's invalid. But it will have to be fixed eventually. And this will be fixed by the general technique for fixing, which is called correction on use, which I'll explain in a few minutes how it works. Okay? So you see what can happen when a node joins, the routing tables, maybe there's other ones with mistakes, but this one will have a mistake. You see it done? Because this first link should go to 14 and not 15. Okay? So that will be a mistake. So when nodes join, the routing tables will start getting mistakes in them. Which is very normal, It's okay, and the routing will still be correct. Because of the predecessor successor, the routing will still be correct, it will just be less efficient. So we have time to fix it. It doesn't have to be fixed instantaneously, but it has to be fixed eventually. Not too long, we don't want to wait too long. Okay? So this is then the third principle I want to explain to you. This is how the routing tables are fixed, which is called correction on use. So the correction on use will fix the routing tables during the normal lookup operations. So if there's a lookup operation, so the lookup will always find it, but if it notices that there's a mistake, if it ends up on the wrong place, it will send a message back and to fix the routing table. And there's 2 ways it can notice mistakes. Okay? So remember, each interval has a single node, which is the responsible node. And this is the one that all the routing from the high level has to go to. Okay? But what if this node fails? Then there's another one that's responsible. So the knowledge of responsible may be erroneous. Okay? So how can we find it out? Well, when a node sends a message to another node during the routing, it can tell me where it's coming from, the number of the node, plus the level it's at, and which selection, which entry it has selected. Okay? And the receiving node then knows all that, and whether it's correct. I'll show you an example of that. And another thing is very simple. If a node joins, and that's a new node in the system, nobody knows that that node exists except for the predecessor and the successor. Eventually, the other nodes have to figure it out. Okay? So if I receive a message from a node that I've never heard of before, then I know that that node exists and I may have to change my routing table. Okay? Okay? So when I do a lookup or insert, so lookup is the get, insert is the put. When I do a lookup or an update from end to end prime, I add some information, piggyback to the message. The level starts level 1, 2, 3. At each level, I have the interval. So I add intervals, two numbers, I and L. And X, I, L, N is the responsible node. That's one that you can actually compute because it's based on the structure of the tree. Each interval has a responsible node, which is basically the first node in there that exists. Okay, so you can compute that one. Okay, so let me show an example of how it works. Okay, here I'm node 1. So here's the system with node 1, 2, 3, 6, 10, 12, and 15. Okay, and I want to do lookup. I want to do lookup of 13. But we have this 14 which has been added, but 1 does not know it yet. Okay? So 1 has its tree as if this one doesn't exist yet. Okay? So node 1, on level 1, we use level 1 interval 3 pointer. L equal 1, I equals 3, will come here. So we'll go to node 15. Okay? But 15 has already talked to 14. Okay? And 15 knows it's not the responsible node anymore. Because 15 has talked to the predecessor. The 14 has joined. Okay? So this is how it works. So node 1 doesn't know that, and node 1 sends a message to node 15. Okay, the purple arrow. But 15 says, no, that's wrong. You're wrong, he says. It's not me you want. It's not me you want, it's this one. So the bad pointer, the 13 is not the one you want. These are not the droids you're looking for this one. Okay? So it sends a message back to node 1 saying there's a candidate, a new candidate for responsible node, which is 14. Why is it a candidate? It might not be the actual one, because maybe another node, maybe there's more nodes coming in. All the 15 knows is that 14 is a better choice than itself. Okay? That it's 15 knows it's not me, and if it's anybody else, it's 14. Maybe 14 is not the right one either. Maybe another node also came in here, and 14 will say it's 13. But eventually, it will converge to the right one. So normally, if there's only one node coming in, then 14 knows it's the responsible one. And then, number 1 in here will fix the routing table to put in 14, and then it will send a message to 14 and we're done. And the routing table is fixed. Okay? Okay, so basically the routing table coming now from node, so here again from 13 you have to go to 14, not 15. What will happen then is that node 1 will send a third message, the green one. Instead of saying, but this message will be also for 13.1.3, but it will be sent to node 14. Okay? The routing table here will now be correct. You see? So 15 sends a message back if it knows there's a mistake. Okay? So whenever we do a lookup, and a node knows that it's not the right one, that it's not the responsible node, and nodes know when they're the responsible node, it sends a message back, and the routing table is fixed. This is happening all the time. So this extra round-trip message here, it only fixes the routing table. Okay? After that, everything's working normally. And this is some measurement on that. So when you do lots of lookups, okay, so assume you have, so this is the ratio of the lookups to the actual system size. So you need to do a lot of them. So the system is 1,000 nodes. Here you do 100,000 lookups, okay? Here you do almost none, you start. So you make 10% changes in the network, which is a lot, huh? You change 10% of the nodes. That means the routing tables have a lot of mistakes in them. So look here at the average route lookup length. In the beginning, it's very high because of all the mistakes. But it always works, huh? Like I told you, the routing table is an optimization. So even if it's degraded, it still works. It's just slower. So here you can see that when there's so many mistakes, 10%, the average length is very high. It starts more than 14. But the more lookups you do, the better it gets. So the more you run the system, you basically converge to correct routing tables, okay? So the two lines are for k is equal to 2, which is chord, and k is equal to 4, which is the example I just showed you. So you see the k equal 4 case has less hops, which is normal, since k is bigger. But both of them are converging to correct. That means as long as there's not too many errors, the system will completely correct the routing tables. By normal lookups, it will correct it. It's like a librarian. When I'm managing books in a library, and somebody puts the book in the wrong place, well, and then someone else asks for the book. The librarian will look for the book, won't find it, will look around until he or she finds the book, and then we'll put the book in the correct place. So that's kind of like this, huh? And the next time someone wants to look up that same book, it will be in the correct place. You see how it works? So it's like correction while you're working. Okay, so you kind of see how this system kind of does the magic. Now, I'm going to show you another algorithm, broadcast. Once you have this beautiful structure with the routing tables, you can do things with it. And one of the things you can do is efficient broadcast. So even if you don't know all the nodes, even if nodes are coming in and leaving, you can do an efficient broadcast because of the structure of the routing tables. Okay? So let me show you that. But I won't show you that today. Today I have to stop early, so I will be stopping in a few minutes because I'm participating in a workshop in New York, which started at 10 o'clock in New York in the morning. That's 4 o'clock here, 6-hour difference, and I am actually leading a session that starts at noon. No, 1 o'clock, I think. I hope no, noon. Yeah, noon. Which makes it 6 o'clock here, which means in 15 minutes. Okay. So I will stop here for today, and next week I'll go again and I'll let you think a little bit about this beautiful self-repair, self-organizing